Calculus, Taylor polynomials, infinite series. What a treat. Special thanks to Kate Yetman. Kate Yetman was sort of our chosen author of the music that we decided to go with this particular morning. And Kate's the daughter of Chris Yetman, who provided the wonderful vocal stylings on that particular track. Chris is a terrific teacher, a very prominent member of the AP Calculus AB and BC community. So Chris, we thank you and your daughter Kate for that wonderful music. And we're going to try our best to feature some of the special talents that a lot of our viewers have shared with us, and boy, we gotten a lot of them. We could make a whole album. So look for that to drop soon, the AP Calculus BC album coming to a music store near you. So I thought what we'll do today, something a little different, because in this time of social isolation, I figured that a lot of music artists are out there kind of sharing their talents a little bit, kind of doing their thing. So I figure instead of learning calculus today, we're going to play some music all day long here for at least the first 45 minutes. So we're going to take some requests. Just drop them in the Twitter and we'll be sure to get to them. Wait a minute, our viewer count's going down. No, don't go away. Come back. No, we'll go back to calculus, I promise. Yeah, let's go ahead and do that. We'll hold that music off for another time. But I tell you what, we are going to bring the guitar back into this lesson because there's a really neat connection between what we're going to talk about today and music. So make sure you stick around for that. But today's lesson is going to primarily deal with 10.5 in the CD. That's the Harmonic Series and P Series. And the idea of these two types of series is going to be featured on this year's AP exam. And then I'm gonna also piggyback on Brian's excellent lesson yesterday about alternating series. And we're going to discuss this idea of how to determine absolute versus conditional convergence. Okay, so that's the agenda for today. Once again, if you want to get a hold of any of the materials that we're using for our sessions, you can just go down into the comments underneath the video, access our Dropbox, and within the folder for the day, you can access the PDF file. Once again, my name is Tony Record. I'm a calculus teacher at Avon High School in Avon, Indiana, just west of Indianapolis here in the good old Midwest. And as you can probably tell, Brian and I are kind of battling a little bit of issues. Some seasonal allergies are upon us. I've got a little bit of warm weather, so we're kind of fighting through that, but we'll make it just fine. So upcoming lessons. Yes, today is April 1st, and that was my April Fool's joke, right? Not a very good April Fool's joke, I suppose. You guys knew I was going to be playing music all day, right? You knew that. So we've got our Harmonic Series and P Series today. I do have the dates correct, finally, here. Thursday, April 2nd. Tomorrow, Brian's going to come back on with comparison tests for convergence. And then I'll wrap up the week Friday with a geometric series. And as you can see, we've got a lot of fun stuff coming up with the week ahead that's going to kind of ease into the idea of the Taylor approximations, polynomials. And then, boy, when we get to April 13th, that's when all the great stuff is going to happen with the BC Calculus review that Brian and I have planned for you. So make sure that you plan for that. Now, to start with this warm-up, I guess I'm not the only bearer of April Fool's jokes, because I think Brian had the ultimate April Fool's joke on me. He certainly gave us a doozy of a warm-up, and he left it on my lap to kind of pick up the pieces. But I want to tell you, this is an excellent problem. It's very well written, but I think what this problem sort of focuses on is not so much the calculus that we have learned and how we can use that to solve it, but it sort of opens the door for us to maybe investigate and think about, are there better ways that we can actually answer some of these questions? And the answer to that is yes. So Brian kind of purposely put this on my lap here as his April Fool's joke for mixing up all of those dates on him yesterday. So he got me. So anyhow, for this particular warm-up, we have this alternating series, as you can all see. And we are asked in part A to use this alternating series to test to show that this series will converge when x is 3. So the very first thing that we might consider doing is saying, okay, well, let's take a look at what does the series look like when x is 3. And we do that. And we get something that looks like this. We just replace the x with 3. So we don't have this power series anymore, right? That has this variable of x. We haven't really talked to you guys about power series. We have this sort of normal, well-behaved alternating series. Now, I'm going to show you a slightly different solution than what is probably available on the Dropbox. Our amazing partner, Ted Gott, did a fantastic job working through a very analytic way to solve this particular warm-up or this AP practice problem from yesterday. I'm going to take maybe a little bit more of an intuitive approach, maybe talk about why we would probably yearn for another kind of a procedure that might make this job a little bit easier. And in my intuitive approach, I can use just a little bit of technology to kind of tie in some ideas together. But the very first thing that we want to do if we're using the alternating series test is determine what the limit is of the non-alternating component as n approaches infinity. So we take a look at that limit, let n approach infinity, and the non-alternating component, basically, it kind of does away with that -1 to the n. Now, we don't want to forget that he's there because he's obviously a part of the problem, but we don't focus in on him when we take this limit in the first step of the alternating series test. And we get something like this. And it's sort of a sad situation when we have a factorial involved in a limit. In fact, it's kind of a sad situation we have factorials involved in calculus in general because factorials just don't play very nicely with calculus. It's very difficult to take derivatives of them. It's very difficult to take integrals of them. So we have to think about this a little bit more intuitively. And if we do let n approach infinity, it's very clear that we are going to get a very large number on the top. We're going to get a very large number in the denominator. You might think, oh, that allows L'Hopital's rule to be used, but again, we can't take a derivative of something that contains a factorial. So one way to think about this, the idea of the partial sums, kind of as we move into part 2, we can certainly think about the partial sums. But as far as this limit is concerned, we don't have that to rely on, so we just have to understand the magnitude of these numbers. So if I kind of move over here to just a list and spreadsheet, this is on the TI Inspire, but this is something that could be done on Excel. It could be done on any kind of calculator if you just push the right buttons in the right sequence and so forth. But I just made a little spreadsheet that allows me to enter some value for n, and I can kind of compare what 3 raised to the 2n is going to become, and then I can compare what 2 times n quantity factorial is going to be. And as we see at the very beginning, the 3 to the 2n, right, which is in column B, that's the numerator, is a little bit bigger. And then it becomes even bigger still. And then all of a sudden, 2 times n factorial begins to catch up a little bit. And then by the time we get n to be 4, 2n quantity factorial is really, really kicking the other guy's rear end, right? So we keep going on and we find out that this 2n factorial is much, much bigger all the way through the problem. So if we continue, if we go back to this, we can kind of deduce that this denominator is growing much, much faster than the numerator. And that's going to give us enough evidence to say that this is going to be equal to 0. If we take a look at the second phase, or the second part of the alternating series test, what we're looking at doing now is showing that the nth plus 1 term is possibly less than or equal to the nth term. We're questioning whether there's truth to that. So we would replace each of these n's with n plus 1. Now notice I will have to distribute the 2 in both instances. So I have 3 raised to the 2n plus 2 over quantity 2n plus 2 factorial. And I'm questioning whether that is less than or equal to 3 to the 2n over quantity 2n factorial. So with this, we do a little bit of manipulation. Let's say I divide both sides by 3 raised to the 2n. And in doing so, I'm going to reduce a bit. 3 to the 2n plus 2 over 3 to the 2n would produce 3 squared, or 9 on the left side. Keep the inequality symbol there. And then if I multiply 2n plus 2 factorial to the right, and I think what I'm going to do off to the side here, I know sometimes students that I work with kind of struggle with this idea just initially, and then once they see it a couple of times, it begins to make sense. But when you have these magnitudes of these factorials in a quotient like this, we can construe the fact that this 2n plus 2 factorial is really the same as 2n plus 2 times the next number beneath it, or less than 2n plus 1, times the next value, one integer value below, which is 2n. And then all of a sudden, if I keep going downward, I could just throw my factorial there. And that's really what 2n plus 2 factorial is equivalent to. And then you can see some cancellation, and then you're left with 2n plus 2 times 2n plus 1. And if I go ahead and expand that, I get something that looks like this. And if I want to investigate this a little bit more, if I want to maybe set this inequality equal to 0, I could subtract the 9 over. And it looks like I've got this, right? I just kind of flipped it around to have all of the variable expressions on the left side. And we have to think about, okay, well, is there going to be a value in where this statement is going to be true all the time from that point forward? And the answer is yes. It doesn't take a very large n to make this work. And just to kind of show you graphically, I've sketched that particular quadratic. Now note, I had to use the variable x just to appease the calculator, but this does graph this parabola that does have some portions of it that lie below the x-axis. But by the time we get to be n equal 1, we can see that we are well above the x-axis, and that's never going to change, right? We want to ensure that we have a position where a value, I should say, where this graph is always going to be above that x-axis and never change. So we've deduced here that the alternating series test does show that this particular series does converge. Now for part B, show that this series converges for all x. Now, this is where we're kind of slipping into something that is very powerful. And I think Brian may have already mentioned how this is a very, very popular Taylor series that normally would be a big focus point on the AP exam, but in 2020 it won't be. But it's nice to kind of investigate that, and then we can revisit this idea a little bit next week when we get into our Taylor polynomial discussion. So in this particular case, we're going to leave this x as an x. So that means our first step would look something like this. We're going to take the limit as n approaches infinity of the nth term without the alternating component. So that would look something like this. Now, because I don't know what the value of x is, I can't, set up some kind of a spreadsheet to kind of do this a little bit more intuitively, but instead I have to think about what I learned from before. And what we learned from before is that factorials are pretty darn powerful. If you take a look at sort of the pecking order, if you have something like x to the second power, we know that if we were to take an exponential version, right, x to some n power, that's probably going to be something that's going to grow a lot faster for most given integer x's when we have an n exponent than just say a squared exponent. But if we were to even apply something like a factorial, then we can probably construe that this is going to grow even faster, as we just indicated. So we have this sort of hierarchy of how things can grow. And there is a test, fortunately, there is a test, and we're going to share that with you next week, that will make kind of considering how the convergence of a series that might look like this can be done a lot faster, and it's called the ratio test. So in this particular case, we know that that denominator is going to grow pretty darn fast, so we're going to go ahead and call him 0. And then for the second part, well, the second part is kind of interesting here, because we're going to do the same thing that we did up here for part 2, but instead of these 3's being located in that particular inequality, we're going to replace those with x's. So what that's going to basically result in is, instead of having this 9 over here, we would have x squared over there. And then the right side is going to be the same as it was before. Okay, Now we're still sort of questioning whether that's true, right? So if we try to set this inequality equal to 0, it's a little strange. All right. Now, I'm not saying that this can't be solved analytically. I think our answer key, Ted, does a fantastic job of walking you through that. And I certainly would encourage you guys to take a peek at that. But there is a way that this can be addressed in a visual fashion. And I'm going to try to do this the best way that I can by looking at yet another graph. And so let me kind of show you what's going on here. This particular graph here is depicting the 4n squared plus 6n plus 2, right? That's what we had normally with that polynomial expansion. But now I'm subtracting that x squared, and I had to call that x1 for the purpose of the calculator here. Remember, these x's are kind of like our n's. Well, I've attached a slider, which is something that you can do with a variety of programs, Desmos, TI Inspire. And if we allow that x1 to be virtually anything, right? There's the 3 that it was before in part A. But if we keep doing that, we find out that we still have this parabola. This parabola is still going to be fairly well behaved, and that as soon as it gets to a certain value here for n, it is going to reside above the x-axis and never change. And that's what that particular second criteria said. At some point, you have to be positive and not change your mind. And that's what we've got. So we can say, because of that, this is a true statement, and we are therefore convergent. Now, part C might look like it's a little bit more complicated because it's kind of drawing upon some very old ideas, but it's not that bad because you've got this function f of x where f prime is now defined as that particular alternating series. And I've got it written in both closed form and open form here. It says determine if f of x has a relative minimum, a relative max, or neither at x equals 0, and give a reason for your answer. Well, we know that in order to have a relative max or min, we first of all have to establish that we have a critical value, right? And that critical value is determined, let's use green here, is determined by taking that derivative and setting it equal to 0. Now remember, as we set this derivative equal to 0, we have to know what the x value is going to be, right? In this particular problem, we know that we're dealing with an x that's equal to 0. So we're trying to figure out, well, when does f prime of 0 equal 0? And then we can go on from there. So if we look at our f prime of x open form, we can just replace all of those x's with 0. And it doesn't take very long for me to figure out that, whoa, a lot of these things are going to go away, aren't they? In fact, every single term after that first term of 1 is going to disappear on us. So f prime of 0 is equal to 1. Now let's think about that. What did we just say? The derivative evaluated at the point that we're trying to determine where there's a max or a min is equal to 1. It's not equal to 0. It's not undefined. It's equal to 1, which means we don't have a critical number there, which means there's neither a max nor a min. So there wasn't a whole lot to that, but it was nice that this problem kind of drew upon some information that was taught very, very early in the course. All right, so let's go ahead and take a look at what's going to be on tap for today. And in this lesson, we are going to introduce a very important and quite common series. It's called the P series. And then we're going to determine the conditions in which a P series will converge or diverge. And then to kind of piggyback on what Brian did yesterday, I'm going to explain the difference between conditional convergence and absolute convergence and sort of bring in this idea of the alternating series back in. What you should already know coming into today, well, by now, hopefully we have a pretty solid understanding of what it means to converge and what it means to diverge. Those words get thrown around all the time this week and next week as well. And we want to make sure that we are fairly comfortable with techniques for evaluating limits. And of course, the alternating series test for convergence that we learned yesterday comes into play quite a bit. So an example of what you might see in a lesson or in a problem set that deals with this particular concept or group of concepts would be, say, a summation from 1 to infinity of the sine of 2n minus 1 times pi over 2 all over n. The question would be, does this series conditionally converge, absolutely converge, or diverge? So that's going to be one of the kinds of questions that we address here in a moment. All right, to get us started, real quick recap on the alternating series. Let's refresh back. Each of these following series, as you can see, can easily be shown to converge because they meet the conditions of the alternating series test, okay? Now that first example that we did, very difficult problem. I don't want you to worry about, especially when you look at the key and you see Ted's wonderful analytic approach, it's very likely that that's something that you're not going to do on the AP exam this year or perhaps any other year. A lot of those things are showing you proofs of some of the items that we're going to potentially expose you to next week. But as far as something like this is a little bit more rudimentary type of alternating series where each one of these is going to converge. And the reason is because whether I take the limit of the first one, the middle one, or the last one, they all have something in common. And if I remove the alternating component, let's say I look at the first one, that limit is certainly going to be equal to 0, right? If I throw in a square root, that doesn't really change the fact that that's going to also equal 0. Or if I were to square that in, it's just going to go to 0 even faster. So you can see that the first criteria of the alternating series test passes pretty quickly, pretty easily. The second criteria is just a matter of determining whether or not the first term, or I'm sorry, the nth plus 1 term, my mistake, is less than or equal to the nth term. And without going through all the motions, because you saw it with the first warm-up, you can see that each one of these is going to behave that way. Each one of these is essentially what is a decreasing series in this particular instance. So these are very quickly recognized as converging by the alternating series test. But it kind of makes you wonder, are they converging because they're alternating, or is there something else that's going on with this? So we're going to get back to that here in just a second. But first, let's go ahead and take care of the initial concept from this particular topic, 10.5, and that's the convergence of a P series. And if you read through this, and if it seems pretty easy, you're thinking it correctly, because this probably is one of the easiest, if not the easiest test for all of the convergence series. There's about 10 convergence tests that a student would typically need to know in a BC class. This year, things are a little different. You need to be responsible for about 4 of those 10, and this is probably going to be the easiest. A P series is pretty easily recognized because you've got this 1 over n to the P form. You might have to do some simplifying to get it there first. And then we just simply take a look at that P, and if that value of P is strictly greater than 1, we know that that series is going to be convergent. That's it. Nothing else you have to do. If that P happens to equal 1 or be less than 1, then we know that that series is going to diverge. And I know that we say we have this extra little restriction here that P is always going to be at least greater than 0. And I think the reason for that is it's fairly trivial if we were to let P be some negative number, because if that was the case, this n to the negative P would have popped up to the numerator. And of course, we don't have any chance to converge at all if we're just adding a series of unbounded numbers like that. So we're going to say that the divergence is going to be for P between 0 and 1, including the 1. So how would you tackle some problems that deal with the P series? Well, really, if you can identify that P, that's about the only thing that you really need to focus on. So here it says determine the following series if they converge or diverge, and identify any values of P. So if we take a look at this first one, you could certainly rewrite this if you had a difficult time determining what the P was. So you would have to understand your rules for your exponents and your indices and so forth. So the cube root of n is nothing more than n to the 1/3 located there in the denominator, right? We want to keep that thing in the denominator. So we look at that and we think, okay, well, what is the P value? Well, P is obviously equal to 1/3. And because P is equal to 1/3, we know that this will diverge. And if you want to be even more specific, more precise about this, you could say this diverges because the P value was between 0 and 1. Okay, it's that simple. P series, piece of cake. Let's look at one more of these. I don't think we need to do all 5. I would certainly love for you guys to take a look at the 3 that we don't do, just to get some extra practice in on your own, and you can always check it with the key that's posted online. So if you take a look at C, we've got in this particular problem a little bit of work to do because we don't quite have this written in the form that we would like. So if we take this into the -2 times into the 1/2, essentially that would just be into the, well, -2 plus a half would be -3/2. And then we can rewrite this so that it looks more like what our P series is supposed to look like by plopping that into the 3/2 into the denominator, giving it a positive exponent. And then we look at that and say, well, wait a minute, 3/2, that's certainly larger than 1, right? So identify our P as 3/2. So based on that, we can say that this series is going to converge. And the reason is because that the P value is strictly greater than 1. All right. Now, let's focus our attention a little bit to this topic in 10.9, which is, like I said, it's a really wonderful extension to what Brian was talking about yesterday. We're going to define what it means to be absolutely and conditionally convergent. So one thing I want to make sure that you're aware of, we are dealing with, for the most part, an alternating series here, but we could apply this in some other instances. So let's take a look at this summation A sub n. The summation is absolutely convergent, right? So the best kind of convergence that we have if the summation of the absolute value of that expression converges. Okay. Now, on the other hand, we have this summation that is conditionally convergent if the summation itself converges, but the summation of the absolute value diverges. I know that that can be very confusing. You got 2 different pieces of this. And when we solve some of the problems, I'm going to try to break it down and really give you a step-by-step process so that you can't get lost in this particular solution. So as we said before, from the previous lesson on alternating series tests, we noticed that if a series does alternate, then sometimes it seems like it has an easier chance of converging. And the reason is because you're adding some positive number and then you're taking away something, which tends to make you a little smaller, right? And then we add something else and then we take away something else. So the potential to converge is there. But when working with an alternating series, we have those both positive and negative terms, and it's kind of natural to wonder, does the series converge because it was alternating, or would it have converged regardless of the alternating component? So if we consider this alternating series from the beginning of the lesson, right, the summation -1 to the n plus 1 over n, we've already determined that this series converges by the alternating series test, okay? We know that it satisfies criteria 1 and it satisfies criteria 2. But would this series still converge if it were not alternating? Well, we certainly know the answer to that because we just talked about P series, and it turns out that this guy right here is a very special version of the P series, right? Where the P value is 1. And if you remember, I'll walk you back here just really quickly. The P series says that we will diverge if the P value was equal to 1. So we seem to have a bit of a conflict here. It's interesting that this guy will diverge, but we know that this guy up here converges. All it took was to add that alternating piece, and we have this different behavior. And when that happens, we have to sort of temper that convergence and call it conditional convergence. And we could spend a whole lesson talking about, well, really, what's one of the differences between something that converges conditionally and absolutely? But one of the things is that you could violate a very important rule in mathematics called the commutative property. In other words, I could take all of the terms, right, all of the individual components that make up that series, add them together, and get some result. But then if I take those same terms, put them in a different order, and add them up again, I get something different, which That's ludicrous, right? We know that 2 plus 3 and 3 plus 2 is always 5, but that doesn't always happen in the world of the alternating series. And because of that, we have this sort of tempered way that we think of convergence. So what this is saying, once again, is that the alternating series, -1 to the n plus 1 over n, is conditionally convergent because that alternating series itself converges. But if we took the series and focused on the absolute value of that nth term expression, we have something that diverges. And those two series are important. They have very special names. And we're going to call the summation of 1 over n the harmonic series. That's when p is 1. And then obviously we have his friend, his alternating counterpart, the alternating harmonic series. And there in the green box, we have just a special sort of homage to that harmonic series. And, if you hear and see the word harmonic, you might kind of think, well, that kind of sounds familiar, especially for those of you that are into music. A lot of my students, I would say half of my students at my school are involved in music in some way or another, whether it's band or orchestra, or they just play music on their own. And I don't know if you ever stopped to think about this, but how does the harmonic series have a relationship between harmonies in music? And it certainly has a very nice relationship. And it turns out that I happen to have my guitar here, so maybe I can kind of share this with you and see what this looks like. So here we go. The harmonic series. Well, one of the ways to think about this is on a stringed instrument like the guitar, we have these things called frets. And if I take a guitar in standard tuning, that's an E string, there's a fret right here. It's called the 12th fret, right? If I count 1, 2, 3, 4, all the way here to 12. Now, it's always funny. I tease my students that play violin, viola, cello, and bass. It's like, you guys are the real musicians because you don't have frets, right? Guitar players like me, we're kind of dumb. We have to have these little frets to know where to put our fingers. But if I put my finger right here, what I have is basically a fretted position that takes this string and cuts it in half, right? The string is sort of mounted right here at what's called the nut, and right here that's called the bridge or the saddle. And right here at the 12th fret is half the distance. Well, what does that mean? Well, that means that's an important note. And it turns out for those of you that play stringed instruments, you might know that this note is an octave higher at the 12th fret. Now, we can apply that a little bit differently. Let's say I fret at the 3rd position, right? That would make, in other words, the string a third as long as it is. Well, that means I have to really kind of count a little bit farther, 13, 14, 15, 16. It's actually here at the 17th fret. And because this is an acoustic guitar, even though it's got a cutaway, it's kind of hard to play really high up on the neck, right? I have to get one of my electric guitars to do that. But right here, I have a third of the length of the string as opposed to the entire length. Now, what I wanted to do with this is kind of change this. If this is now at the 17th fret, if I go 12 frets this way, I would be back here at the 7th fret, let's say. All right. So at the 7th fret, I now am 2/3 the string that's being played, 1/3 that's being muted. What's the big deal here at the 7th fret? Well, this happens to be a B note. And I can find this B note a lot of different places on the guitar. One of them is right here on the A string at the 2nd fret. Notice these are essentially the same note. Now, where's this all going? That's where harmonies come into play. These two notes would be in harmony. They sound pretty good together. And in music, we call it a fifth, right? Now, I'm not going to go into a long music theory lesson about the circle of fifths, but that's a pretty good note. And fifths are nice chords to play because they make up a lot of good rock songs, right? So there's your little music lesson for the day. And, we're not going to do much more. Yeah, we're not going to play that. So hopefully for those of you who have an interest in music, you can see that there's a nice connection between calculus and things in the music world. And the nice thing is that the history of math is so intriguing, and I really would encourage you guys to investigate some of these stories, and you can find them probably on the internet somewhere if you can get to a reliable source. But it's it's really interesting when you think about the person who first connected the idea of like a harmonic series to music, and it's not the person that you probably would attribute this to, but it was Pythagoras was one of the first people to make that connection. And we're talking about somebody who did all of his mathematics in 500 BC. Now, I doubt Pythagoras had a really cool Taylor guitar around, but they had other kind of stringed instruments like lutes and maybe the precursors to the dulcimer. So there's your little music lesson with mathematics for the day. So what we've got here in the next group of guided practice problems, I call it the kitchen sink of alternating series. So I just wanted to pick one of these here and work this one with you. In fact, I think I'm going to pick part C. Let's go on to part C. It says determine if the following series are absolutely conditionally convergent, conditionally convergent or divergent. So the very first thing that we need to do with this is focus on the limit, focus on the summation, I should say, of the absolute value. I want to figure out what's going on. What is going on with this guy? Right? So if we think about the role that those absolute values play, well, certainly they just kind of wipe away the alternating term, the alternating component, I should say, 1 over the square root of n. And I have something like that. And then we have to think about, okay, what do we have on our hands here? Well, we have a p series, right? The p is obviously equivalent to 1/2. That 1/2 is less than 1, right? So we have a divergent situation. Now, what does that mean? Well, all it means is that we've lost any chance of being absolutely convergent, right? We don't want to give up on the problem and say, oh, we're completely divergent all the way around, because that may not be the case. We've just lost absolute convergence, right? Now what we have to do is go into the alternating series test. So we still use that concept from yesterday, which, if you remember, has 2 parts to it. That's why we reviewed it pretty heavily at the beginning of this video. And the first part is, what is this limit doing of the non-alternating component, which is just the 1 over the square root of n. And as n grows really big, we can see that this is going to be 0, of course. And then we go into the second phase of the test, which is the nth plus 1 term of this non-alternating component less than or equal to the nth term? So I'm just going to simply replace the n with n plus 1 and question whether or not this is a true statement. And it's very likely, just from that stage, you can probably use some slight intuition to gather that this is a true statement. Of course, if you do cross multiply, whoops, I should put a square root under that, over that. If you do cross multiply, you just have to make sure that the product that you put on the left side is the product that involves the numerator of the left side. And I would have something like this, I suppose, after we cross multiply. Let's say we want to continue this, we could square both sides, but with each passing step, subtracting the n from both sides, you're going to get to a place where you feel pretty confident, right? I think we can probably throw this in front of an elementary school age student to say, hey, is this a true statement? As long as they knew what this inequality symbol meant. So we do check both of those particular criteria, which means the AST is saying that this thing still converges, but the summation of the absolute value said otherwise. That's the situation where we would say that this is going to converge conditionally, or you could say conditionally convergent. Okay, so there are 3 different things that obviously can happen in this situation. Okay. There are a lot of problems in this guided practice. Brian purposely wanted to write several of these so that you can get some extended practice with this, and they're all great. And each one just has a little bit of a different nuance to them. So I certainly would invite you to try some of these and certainly check them with the key that's now posted. Let's go ahead and take a look at a slightly different approach to this idea of absolute and conditional convergence. It's the same kind of concept, but it's going to have you sort of think in a slightly different level. So we got it. I call it the alternating series roundup. Yeehaw. So what I've got here is 6 different series, right? A through F. And we have a question that asks to find a value of K such that the summation -1 to the n of A sub n is conditionally convergent, but yet the summation -1 to n of B sub n is absolutely convergent. And I'd like you guys to kind of think about this. I'm going to give you a minute or so. And about halfway through that minute, you'll hear some music play. If it's too loud, you can just kind of lower your volume. And then we'll see if we can check your answer. Take a look at this one. All right, wonderful. That music is compliments of Kareem, one of our listeners that submitted yesterday. Thank you for that. And if we take a look at our solution, find a value of K such that this particular series is conditionally convergent. Well, what we're going to do here is think about what A sub n is. Well, A sub n is our lead-off series over here, 1 over n to the K. So if you have to rewrite that, that's certainly acceptable. You know, you can get definitely a better look on what this thing is really doing. And we noticed that, okay, well, that's kind of our typical P series form, I suppose. And we learned that this alternating version of this P series will indeed converge conditionally as long as that K value does not exceed 1, right? We want this K value to be less than or equal to 1. Now, we also know that the K is going to be greater than 0 at the same time. So we'll kind of temper that a little bit. But we know that we have this K that has to be less than or equal to 1. But if we look over here on the other series, and I might go ahead and write him up to get a better look at what he's doing. And -1 to the n, there's the alternating component. And then what's B of n defined as? Well, Brian's defined B of n to be this an squared. So if you can picture squaring that particular expression, the 1 squared is not going to change. He's still a 1. And then n to the k squared allows us to multiply those 2 exponents to get 2 times k. And now we can get a little bit better handle about what's happening. Now, again, we want to make sure that this 2k, in order for this to absolutely converge, right? We want this to be absolutely convergent. We know that that has to be greater than 1. And we're talking strictly greater than 1, right? We don't want it to conditionally converge and let 2k equal 1. So if we solve this, we have k is greater than 1/2, okay? Now, you'll notice that we sort of have a range here, right? We've got k being less than or equal to 1 on this side, and we have k being greater than 1/2 on this side. And what we want to do is put those 2 ideas together, and essentially we're going to find their intersection is what we want. So we have to think about all the values of k that satisfy this inequality and this inequality and this inequality. And so if you put those 2 ideas together, it's any k that's strictly greater than the half, right? Half is less than k, but at the same time, we cannot be any larger than 1. So we can be equal to 1, and of course less than 1. And that would be your range of k's there. But as you can see, if you have the document in front of you, there are 3 other versions of this that kind of filter in the other series and ask slightly different questions about finding the maximum value of k. It's an excellent problem. In part C, we're going to know that the first series is absolutely convergent, determine if the second series that involves the f sub n is either absolute, conditionally convergent, or divergent. And then we have another part D here that wants to determine which alternating series has to be absolutely convergent, given the condition here for the alternating CN series diverging. So there's a lot of great things going on with this problem. It's a very well-written problem by Brian. All right, so we have another phase here, this check for understanding, that again, we wanted to throw a few more problems at you that dealt with the idea of the alternating series as an absolute convergence and conditional convergence, because it does take a while to practice these. I tend to give my students a few extra of these problems because it does have 2 different steps that you have to kind of isolate on. So again, we invite you to take a look at practice 2. We have, I think, 4 more there, A, B, C, D, and we've really threw in a great one here with D. I'd like to certainly to give that one some attention because of the idea of the piecewise function approach. So if we summarize what we have been doing today, we find that our enduring understanding really hasn't changed. We're applying limits, and we know that applying them may allow us to determine, the finite sum of an infinitely many-termed particular series. And the key takeaway here, well, the p-series. The p-series test is one of the very easiest things that we will probably learn in BC calculus. And we know that we will converge if that p-value is greater than 1 and diverge if it's between 0 and 1, inclusive with 1. And then we learned our alternating series test will allow us to extend it to figure out absolute convergence and conditional convergence by these 2 criteria that have been mentioned frequently throughout this particular video. Some of the common errors, misconceptions, or pitfalls: you want to always be careful to simplify your exponents when working with the p-series. It's probably likely that that's what you would encounter most of the time on a traditional AP exam. So do your algebra correctly as always. And then remember that alternating series can converge in 2 different ways. It's always best to start by determining the behavior of the series of the absolute value of that nth term expression first. And then once you've determined if that's convergent or divergent, then you can go ahead and apply the alternating series test. All right. Your AP exam practice problem, your other homework assignment for tonight, right? What else are you going to do, right? Lots of good calculus practice that you can do between now and tomorrow. But we're going to define a sub n to be 1 over n to the k plus 1, where k is a constant. And in part A, let's let that k be a half, and let's have you use the alternating series test to show that that particular series does indeed converge. And then extend to determine if that series converges conditionally, absolutely. Okay, which of the 2? And then in part B, we're going to define a new nth term expression, b of n, as a of square root of n. Let's find all the integer values of k so that this new alternating series converges only conditionally. And then in part C, appropriately, we're going to define another nth term expression, c of n, to be a of n to the negative 2k. In this problem, we want you to show that there is no real k value, so that this series is the harmonic series. So there's your AP exam practice for the night. And as always, we want to make sure that you, and not just you, but your friends, have wonderful access to the different resources that the College Board is providing. And of course, when it comes time to take the exam, we want to make sure that everybody has the same equitable experience so that they can have the most success possible. So please reach out, cb.org/tech, if you or friends have any questions about how you can better obtain the various pieces of equipment, the various services that you can gain access to these wonderful resources. Our tweet out really quickly for our AP Teachers Rock, right? We're still doing that. Keep them coming. So as far as the AP Teachers Rocking, we are recognizing this particular teacher. Thanks for the quality live AP sessions. My AP Calculus teacher is so knowledgeable and prepared, is willing to reach out and help all of our students and is truly an amazing person and a teacher overall. I couldn't be more thankful. And I tell you what, that's a teacher I would certainly love to work with at my school. So thanks for that. And as far as AP students rocking, we actually have a good friend of ours. We're going to have a shout out to Brian and I's friend from Houston, Cedric French, who's an excellent advanced placement calc teacher down in the Lone Star State. And he says that he's very happy that my students are working hard and preparing for the AP Calculus exam. This is a tough time for everyone, and it certainly is. And you know, we're going to leave this quote, and I think this quote says, you know, everything that we needed to say. You know, you guys are the true dreamers. Keep working, keep fighting. You guys can do this. We're going to get through this together. And that wraps it up. Tomorrow we got Brian coming in for a great session over the comparison tests, and that's going to lead into the end of the week for the geometric series. So without further ado, we're going to sign off now. We want you to have a great day. Please keep safe, keep healthy, and keep learning.